Questions 21 through 25 on the 2016 Grade 11 Fermat Math Contest. Box 1 contains 1 gold marble and 1 black marble. Box 2 contains 1 gold marble and 2 black marbles. Box 3 contains 1 gold, 3 black. Whenever a marble is chosen randomly from one of the boxes, each marble in that box is equally likely to be chosen. A marble is randomly chosen from box 1 and placed in box 2. Then a marble is randomly chosen from box 2 and placed in box 3. Finally, a marble is randomly selected from box 3. What is the probability that the marble chosen from box 3 is gold? All right, so we have a few scenarios. We have gold, gold, black, black, gold, black, black, black. All right, now we just have to look at the different scenarios. We have to choose from box 1. This is box 1, box 2, and box 3. We can put them in little boxes if you'd like. And we've got to choose 1 from box 1, put it in box 2, choose something from box 2, put it in box 3, and then finally choose 1 from box 3. And our goal is to ensure that the box 3 produces a gold. So this one that we choose is gold. So the other two can be a combination. It can be either gold, gold, like that, or it can be black, black, and then gold, or it can be gold, black, or black, gold. So for each of these 4 scenarios, we'll figure out a probability, and at the end, we'll add all the probabilities up. Okay, so the first one, if I'm choosing a gold from this, the probability of that happening is a half. Then gold goes into this box, so that box now becomes basically gold, gold, black, black. And from this, I have to choose a gold. Well, there's a half probability of that, 2 out of 4. And then when that happens, this box here now becomes gold, gold, black, black, black. And the probability of choosing a gold from this is 2 out of 5. So I've got to multiply these, and when I do, I get 1 out of 10. So 1 out of 10 is the probability for that scenario, gold, gold, gold. So we do pretty much the same thing for the other scenarios. So now we get to this one, choosing a black from here, 1/2 probability. When you do the next box, box 2 becomes gold, black, black, black. And then from here, choosing a black has a 3 out of 4 probability. And then when you do, the next box becomes gold, black, 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 black. Choosing gold from here is a 1 out of 5 probability. Multiplying these numbers, you get 3 over 40. So there we go, 3 out of 40. Okay, by now you're an expert, so I'll just fill in the numbers. You don't need me to walk you through it. So this is a half. This is going to be GGBB. This will be a half. This will be GBBBB. And therefore this will be a 1/5. Multiplying these numbers, we get 1 over 20. And then the last one, this one, we have a half. Then it will be GBBB. Getting a G from here, 1/4 probability. Then it will be GGBBB. Getting a G from here, 2 out of 5 probability. Multiplying these, we get 1 over 20 when you reduce it to lowest terms. Now I've got to add up these guys. This, 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 and this. When you add those 4 fractions and reduce to lowest terms if you need to, it will be 11 over 40. And that is the answer to number 21, choice A. If x and y are real numbers, the minimum possible value of the expression is, well, the first thing I'd like to do is expand it. And when I do, I get x squared plus 6x plus 9 plus 2y squared minus 8y plus 8 plus 4x squared minus 56x plus 196 plus y squared plus 8y plus 16. Collecting like terms, I will get 5x squared minus 50x plus 205 plus 3y squared plus 24. And factoring out a 5, I get x squared minus 10x plus 41. And on this side, not much I can do here. Yeah, I'll just leave it like this. Now at this point, this has to be a positive number, right? Anything squared will be positive. So the lowest it can be is 0, and that happens when y is 0. We're trying to find the minimum. So I'm pretty sure that that will be 0 as a minimum. And then this is set as 24. That's just a constant. So now I've got to pay attention to this guy. And I am sure by grade 11, you know that to find max min, you complete the square. And of course, this is before calculus, because in calculus there's another method, but we're not going to use calculus. All right, how do you complete the square? Well, you take half of this and you square it. So half of that is negative 5. If you square negative 5, it becomes 25. But you have to immediately subtract it, and don't forget about that, 41. That's called completing the square, and the rest is the same. Now, the reason we did that is because those three terms will factor very nicely to x minus 5 squared. And then these 2 times 5, you have to kick it out of the brackets. What's that? 41 minus 25, 16. 16 times 5 is 80. So plus 80 plus y squared, 3y squared, plus 24. Okay, so this tells me that when x is 5, that is when we have the minimum value. And that minimum value, if you just look at this part, is 80. And then we had previously concluded that y would be 0 in order to make that minimum. So we substitute in those two values. When x is 5 and when y is 0, all we are left with is 80 plus 24, and that is 104. That's the minimum value. So number 22, the answer is E. Seven coins of 3 different sizes are placed flat on a table arranged as shown in the diagram. Each coin, except the center one, touches 3 other coins. The center coin touches all of the other coins. If the coins labeled C3 have a radius of 3 and those labeled C2 have a radius of 2, then the radius of the coin labeled X is closest to. Well, this diagram is at the heart of the question, so I will blow it up and join all the centers in approximately the best way that I can. So here we go. And once I do, I will try to get some sort of relationship. And my gut instinct is that it's not going to be Pythagoras, because I don't think there's any right angles here. And I think this pretty much is the right way of connecting all the centers, and that's it. Okay, that's not so bad. And hopefully you can see that. I know there's C3s and C2s all over the place, which makes it a little bit confusing, but hopefully this will be clear. Now, the good news is, in my opinion, we can just figure out this whole question with just cosine law. And cosine law, in case you don't know, which I'm certain you do, by grade 11, is that if you have any triangle and you have the labeled A, B, C, and this is, say, theta, opposite the C, C squared would be equal to A squared plus B squared minus 2A times B cos theta, like that. So we are going to use that pretty much throughout this diagram, cosine law. So first, let's use it here. Let's call this theta 1. And this side is 3 and 3. This side is 3 and 2. Those are the radii, and this is 3 and 2. So we can use the cosine law. It would be, let's see here, 6 squared is equal to 5 squared plus 5 squared minus 2 times 5 times 5 cos of theta 1. Correct? So put everything on one side, and we get here 50 cos theta 1 is equal to 25 minus 36, which is 14. So that means the cos of theta 1 is equal to 14 over 50. And therefore, when you take out your calculator and figure this out, theta 1 is equal to 73.7397. I think going to 4 decimal places is good enough. All right, so that was pretty straightforward, in my opinion. So now we know that this is theta 1. This is also theta 1 because those are the same triangles in terms of dimensions. Now let's try to figure out these angles. Those are going to be the same because those involve triangles of the same dimensions. So I'll call it theta 2 and theta 2, those two angles. Again, cosine law. Let's do it this time on this triangle. This is 2, this is 2, this is 2, this is 3, this is 2, this is 3. All right. Again, 5 squared is equal to 4 squared plus 5 squared minus 2 times 4 times 5 cos theta 2. So that means 40 cos theta 2 is equal to 16. Cos theta 2 is 16 over 40. And therefore, theta 2, when you do this with your calculator, 66.4218 approximately. All right, great. So now we get to this guy. These two I will call theta 3. They're both the same because they are part of two identical triangles. Now, one thing I know for sure is that all of those, if you add them all up, would equal 360. So 2 times theta 1 plus 2 times theta 2 plus 2 times theta 3 would equal 360. So divide through by 2, theta 1 plus theta 2 plus theta 3 would equal 180. Well, theta 1 is right here and theta 2 is right there. Substitute those in and solve for theta 3. And when you do, you get theta 3 is equal to approximately 39.8385. All right. We are now down to the final step. Final step, use this triangle and the cosine law. So this will be 2, this will be 2, 2. I will call the radius x, 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 and 2. Okay, so let's use the final cosine law. All right, let's be careful here. 2 plus x squared is equal to 4 squared plus 2 plus x squared minus 2 times 2 plus x times 4 cos of theta 3. All right. Good news is that cancels with that. So put the other guy on the other side, and we get 8 times 2 plus x cos theta 3 is equal to 16. So that means that we can substitute in this guy. So that means 2 plus x is equal to 16 divided by 8 is 2. So that will be 2 over cos of theta 3. Well, theta 3 is 39.8385, like that. All right. And when you do this, calculation is 2.6046 approximately, and that's 2 plus x. So therefore, x would be 0.6046 approximately. And that represents the radius of that small circle x. 0.6046. The closest to that is choice D. For any real number x, x bracket denotes the largest integer less than or equal to x. For example, 4.2 bracket is equal to 4, 0.9 bracket is equal to 0. If S is the sum of all integers k, with k between 1 and 999,999 inclusive, and for which k is divisible by the square root of k bracket, then S equals. What we need to do is make a table and see if that table gives us some sort of pattern. And hopefully the pattern will come sooner rather than later. Here we go. So I'm not going to bore you to death by talking you through every single one. This calculation is fairly straightforward. So I'm just going to put in the values. So if it's 1, it'll be 1. If it's 2, it'll be 2, and so on. But I encourage you to make this table. And when you do, you'll be able to, I'm confident, be able to find a pattern. So let's fill it in and let's then talk about it. All right. So just in case you're wondering what I'm doing, let's just illustrate for a couple. When k is 9, basically following this formula, k over the square root of k bracket. So when k is 9, it'd be 9 over the square root of k bracket. 9 over the square root of 9 is 3, and therefore that's just 9 over 3. And that's why that's equal to 3, right there. Let's do it now for 10. When 10 is equal to k, you get 10 over the square root of 10 bracket, and that's 10. Square root of 10 is approximately 3 point something. I don't know what is it, 3.1 maybe. So when you take the bracket of that, it's just 3. So that's how you got 10 over 3. Okay, so it's nothing earth-shattering. And that basically illustrates whether k is divisible by the square root of k bracket or not. And if it's an integer, it is. If it's not an integer, then I will circle them, because those ones we will not include in our sum. The sum is only those for which k is divisible by the square root of k bracket. And those ones are, for example, the ones that are integers, like that. So that's how we will make this table. So here we go. Let's just keep going. Okay, so it's all filled out. I did it until 50. So now what we do is let's circle the ones that we are not going to be using. The ones that this showed that it's not divisible. It gave a non-integer value. And then once those are gone, eliminated, let's look at the remaining ones and see if the remaining ones show us any kind of pattern. All right, so these ones are all gone. There we go. Okay, so what's left? The first few over here, in my opinion, doesn't really give much of a pattern, nothing really consistent. I like coming in from the other end. When I look at it from the other end, it's a little bit more clearer. It's clear to me because that's a perfect square. That's a perfect square. So is that. So is that. So is that. And so is that. And then watch. Before each perfect square, it looks like there's another one that works. You see that? So 36 and then one before it, 25 and the one before it, 16 and the one before it, 9 and the one before it, 4 and the one before it. So that's pretty good. Okay. So I think, I'm going to write it down here, that numbers that are of the form m squared, perfect squared, and then 1 before it, m squared minus 1. Okay. But I still got a few more that haven't been circled. So for example, 42, or 30, or 20, or 12. What kind of a formula do I make for those? And after thinking about it for a little bit, it looks like those ones are m squared minus m. Yeah, because this is going to be 7 squared minus 7, 6 squared minus 6. Yeah, that'll work. 5 squared minus 5, and so on. Okay, so these are my forms. Let's test this out. So I think I sort of verbally tested it out. Let's say when m is 5, this will be 25, this will be 24, and this will be 25 minus 5, which is 20. Yep, 25, 24, and 20. And similarly for all the values, it will work. Okay, great. I got a pattern. So all the k's are of these forms. Now, we are going from 1 all the way up until, well, not 50. We're going up a lot higher than that. We're going to this 99999 number. All right. So that means that if this is my m squared, I've got to figure out what is m. So I'll just do it on the side here. M squared, the highest it can go up to is this. So when I take the square root, I get m is equal to 999 point something, but I've got to use integer values because they were clear that they're all integers. All right. So that means my sum, S, is basically all the sums from m going from 1 to 999 of these three guys. So m squared plus m squared minus 1 plus m squared minus m. And that's it. So if I can figure out that, I'll be in business. And then at the end, I'll just double check to see if I've done this properly. Okay, so let's combine this before I make the summation. M from 1 to 999. I can combine 3m squared minus m minus 1 like that. And then I can break it up 3m going from 1 to 999 for m squared minus the sum from m going from 1 to 999 of m, and then minus the sum from m equals 1 to 999 of 1. Okay, well, this is where some of those formulas come in. One of these formulas you guys know, this one, most people will remember, 1 plus 2 plus 3 plus ... all the way until m is equal to m times m plus 1 over 2. But the other one, which is 1 squared plus 2 squared plus 3 squared ... the sum of the squares, that's a lesser known formula. Some of you remember it, some of you don't. I'll tell you what it is. It's m times m plus 1 times 2m plus 1 all over 6. All right, so that's what you're going to use. Okay, I think we're making some excellent progress here. So let's use this one now. Using this formula here, it would be 999 times 999 plus 1, which is 1,000, times 2 times 999 plus 1. So times 2 times 999 plus 1 all over 6. Okay, now let's do this guy. That is going to be minus, that's this formula over here. So that's 999 times 1,000 divided by 2. And then this one is just the sum of 999 ones. So that's just minus 999. And that's it. Okay, great. Now let's do this number crunching. 3 times 332833500 minus 499,500 minus 999. And this whole thing becomes 998,000,001. 998,000,001. Okay, let's go back and look at the answer choices. That number was 998,000,001. It's not one of the answer choices. And I'm happy that it's not, because if it was, I would have circled it and moved on. Because that is incomplete. We've done everything right so far, but there's 2 numbers we're missing. So, okay, well, I don't understand. Why would we be missing anything? Well, here's the story. Everything we've done so far is perfect. But we only went up to 999 for m, which is fine because that's what the limit was. But let's say m is 1,000. Let's see if we can squeeze in a few more numbers. If m is 1,000, what's m squared? Well, that's a million, right? Okay. What about m? This guy right here. The first one, m squared. The next one is m squared minus 1. Well, m squared minus 1 would be 999,999, like that. And then what about this guy? M squared minus m, when m is 1,000. It would be 999,000. Now what we have to do is see if any of these numbers fall within our range. And remember, our range was right here, between 1 and 999,999. Okay, well, the range was m or k, whatever letter you want to use, between these two numbers. Well, this is not, but this is, and so is this. So that means these two numbers I've got to also include in my sum. So no problem. The sum that we calculated, add the 999,999, and also add the 999,000. Those are the only two additional numbers that we need to include. And when you add up these three, you get 999,999,000. And that is indeed one of the answer choices. 999,999,000 is choice C for this great question, number 24. The set A 1, 2 until 2045 contains 2045 elements. A subset S of A is called triple free if no element of S equals 3 times another element of X. For example, 1, 2, 4, 5, 10, 2, 0, 4, 3 is triple free, but 1, 2, 4, 5, 10, 6, 8, 1, 2, 0, 4, 3 is not triple free. The triple free subsets of A that contain the largest number of elements contain exactly 1, 5, 3, 5 elements. They are n triple free subsets of A that contain exactly 1, 5, 3, 5 elements. The integer n can be written in the form p to the power of a, q to the power of b, where p and q are distinct prime numbers and a and b are positive integers. If n capital is equal to p squared plus q squared plus a squared plus b squared, then the last three digits of capital N are. This question can be simplified, and we will do it in that simple way. The first thing, of course, is to understand that once you find the value of n, the rest is a piece of cake, because then you just have to deal with this algebra, and that's very easy. So we will concentrate really on just the first part of the question, concentrating on trying to find the value of this n. So first, let's start off with a small subset. That's a very big one, from 1 to 2045. It would take forever to explain and would become very confusing very quickly. So let's start off with a simple one with only 9 digits. 1, 2, 3, 4, 5, 6, 7, 8, 9. So in this case, my k is 9, k representing the number of terms. Now my goal is to find triple free subsets. So triple free subsets from the definition are basically a subset where no element is 3 times another. So for example, I can't put 3 and 9 in a subset because 9 is 3 times 3. So I've got to make subsets that are triple free. The strategy is as follows, and once you understand the strategy, the question becomes a lot easier. Here we go. What you do is you break up this into different groups. The first group starting with 1 and triples. So 1 times 3. 3 times 3, like that. That's the first group. Then you go to the next number, 2, and do the same thing. 2 times 3 is 6. 6 times 3 is 18, but I don't need to worry about 18 because I'm only going up to 9. All right, let's keep going. Next one would be 3. Well, 3 is already included. Next one would be 4. 4 times 3 is 12. Well, that means 4 just appears by itself. 5 appears by itself, so does 6, and so does 7. Well, 6 actually I already have here, so don't include 6. So as you can see, you got to make sure you don't include things that have already been included. So these are my subsets. Now, to make a triple free, I have to choose one or more from each of these groups. I have to choose the max because the key here is right here. The largest number of elements, that is the key. I have to make the subsets have the maximum amount. So I have to choose the maximum from each subset. From here, I can only choose one. I can only choose one number. Here, I can only choose one number. Here, I can only choose one number. But from here, I've got two choices, either the 2 or the 6. I got two choices. From here, it's not tricky, but you just have to do a little bit of thinking. What can I choose from here? Remember, I've got to choose it in a way so that I make the maximum. Well, I can't choose 3 and 9 because 9 is 3 times 3. I can't choose 3 and 1. Those two can't be together. But I can choose 1 and 9. And there's only one way of doing that. Now you say, well, what about 1, 3, and 9? I can't do that because 9 is 3 times 3. And you say, well, what about just 3 by itself? No, because that would not make it the largest. I have to make it the largest. I'm forced to make the largest subset. I have to choose the most numbers from each of those subsets. So then what you do is you multiply these guys right here. And that gives you the total. So in this case, it's just 2. So what that means is that when k equals 9, I have 2 triple free subsets. And since there's only 2, we can just list them. We can easily list them 1, 9, 2, 4, 5, 7, 8, and 1, 9, 6, 4, 5, 7, 8. I didn't write them in chronological order. I'm just going by these subsets. Okay? So hopefully, with a very small example, you're kind of getting how this works. Now let's move up, not to the big one. Let's move up to a slightly bigger example. K equals 27. Now, I've got 1, 2, 3, and so on, right? All the way up until 26, 27. That's my big set. And then I've got to do the subsets, just like how I did here. Okay, starting with 1. 1, 3, 9, 27. Then let's go to 2. 2, 6, 18. Remember, I got to create these sets. 3 is already included. 4, multiply by 3, 12, and then that's it. Can't go to 36 because my list only goes up to 27. 5 and 15, right? 5 times 3 is 15. 6 is already there. 7, yeah, that will be good. 7 times 3 is 21. 8, yes, 8 times 3 is 24. 9's already there. 10 times 3 is 30, but 30 goes beyond, so 10's going to appear by itself. And so will 11, so will 13. Skip over 12 because that's already there. So will 14, so will 16, 17, 19, 20, 22, 23, 24, and 26. Make sure I skip over ones that have already been included. Now, as we did before, let's figure out how many do we get. Well, from each of these individuals, you can only choose one, right? So 1, 1, 1, there's only one to choose from each of those subsets since there's only one number in the subset. But with these guys, there's 2. There's 2, 2, 2, and so on. Now we get to this guy, and as before, we can only choose 2 and 18. And I think I had explained that sort of in the same way there. When there's 3 elements, you can only choose it in one way, and that is you have to choose the 2 on the opposite ends. You can't choose, obviously, 8 and 16 because 18 is 3 times 6. You can't choose the 6 and 2 because 6 is 3 times 2. And you can't choose the 6 by itself, even though it's valid, because we want to make the maximum amount of terms in that subset, as I had previously explained. Now we come to this guy. This is new. Okay, well, how do I select this? Okay, well, I can select the 1 and the 9. That's valid. I can select the 3 and the 27. And I can select the 1 and the 27. All of these 3 are fine. So there's 3 ways to select from there. I can't select 1 by itself because, as previously explained, I've got to choose the maximum number of elements. I can't select 3. There's no combination of 3 that I could select because they would break the rule that one element is 3 times the other. And I obviously can't select 4. So now I got to multiply this by this, by this, by this, by this. The good news is the 1s don't contribute to the product, so the 1s can be ignored. So that means I've got 3 times 2 to the power of 4, and that is 48. So that means there's 48 triple free subsets when k is equal to 27. And also, I hope you can notice that this number is in that form that they gave right here, p to the a, q to the b. So q to the b. So to calculate n, you just have to figure out p squared plus q squared plus a squared plus b squared, and that's very easy to do. Okay, so now that we've done 2 examples, one with k equals 9, one with k equals 27, I think we are ready to tackle the big guy. So here we go. So now we're going for the big one, all the way to 2045. So remember, 1, 2, 3, all the way until 2045. We have to now create the system. And in this case, k is equal to 2045. So here we go. Just like before. Start with 1, and then we have 3, 9, 27, 81, 243, and 729. And then anything above that, it would exceed the 2045. Now, here I'm going to write how many elements there are. And in this case, 1, 2, 3, 4, 5, 6, 7. So 7 will go here. And then here, I'll write how many, the number of such subsets. Well, I have to fill out the list first before I figure out how many there are. Let's try with 2. 2, 6, 18, 54, 162, 486, and 1458. Okay, that's another 7. And then let's go to the next one. Skip over 3 because 3's are already included. The general rule would be that nothing in the first column would ever be a multiple of 3 because those will already have been included. So just keep that in mind. That's actually a pretty important rule. Okay, with 4, 12, 36, 108, 324, and 972. Okay, well, this is 1, 2, 3, 4, 5, 6. Oh, okay. So that means we are now down to 6. So that means the ones that have 7 elements, there's only 2 of them. All right, so that is how we're going to do this. Now, I know it may seem like extremely time-consuming, but the good news is that it gets quicker. And you have to do a little bit of number crunching. So you make these lists as follows. So these ones you can continue. I'll just write them out. And as you continue to make this list, you find out quickly that you only have 4. that have 6 elements in it. The next ones have 5 elements. And then you just continue to make this list, dot, 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 like that. And then you'll get to 25, 75, 225, 675, and then 2025. This will be the last one of 5 elements. And you can count these up. There's not that many. There's only 11. Now you say, well, I actually see that there's more than 11. I see 16. How did you get 11? Well, here's a little bit of a trick you can use to get that 11. What you do is you take this number, 25, subtract from it 1 below that. So that's 9. And that gives you 16. Yes, there's 16 numbers, but we cannot include multiples of 3. So how many multiples of 3 are there among 16 numbers? Well, it would be 16 divided by 3. And just like the previous question, you have to take only the integer value. So it would be 16 minus 16 divided by 3 bracket, and that's 16 minus 5, which is 11. So as previously, I got 11. And that's a quick way of doing it. And then you just keep doing this. You just keep going like this all the way through. So same thing. So now we've done the 7 element sets, the 6 element sets, the 5 element sets. Now probably we're going to get down to 4 element sets. 26, 78, 234, and 702. And that is indeed 4 elements. And then you dot, 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 keep going until you get to the last one. That's 474. And that is going to be a 4 element set. And how many are there? Well, this is where you use your fancy trick. 74 minus 25. All right, so that is 49. And then 49 minus 49 divided by 3, the integer value. And that will give me 49 minus 16, which is 33. All right, great. Let's keep going. Now I'm at 76, because remember, 75 is a multiple of 3, and it's already here, so I can't include it again. So a little bit of thinking involved here. Not an easy question, but completely realistic. Okay, this is a 3 element set. And similarly, dot, 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 you keep going until you don't get any more 3 element sets. And 227 is the last one that gives you 3 elements. And now we have to figure out how many of them were 3 elements. Okay, 227 minus 76. 75, not 76. Remember, it's got to be 1 less. Okay, and that is 152. And then you do 152 minus 152 divided by 3, the integer value. And that is going to be 152 minus 50, so 102. All right, let's keep going. 228, I believe, is right here, so can't use it again. It's a multiple of 3. So we got to start with 229 and 687. So now we're down to 2. And then the biggest one is 680, 2040. And then that's it. All right. So again, 680 minus 228. And that is 452. And then, of course, 452 minus 452 divided by 3, the integer value. And that gives me 452 minus 150, so 302. All right. Now, we have to figure out one final column of a table. And that is, for each of these, what is the maximum? So I guess what I'm really talking about is choices. How many choices? What are the choices? So I'll start off with this end of the table. I think it's a little bit easier to explain. So when you only have 2 elements, you can either choose this guy or this guy. So for each of those, you got 2 choices. So I'll just put 2 right here. Okay. When there's 3 elements, if you remember, there's only 1 choice. And for example, you can only choose 227 and 2043. That's it, as previously explained. When there's 4, I think I had done that one too. You can have 3 choices. For example, if this was the subset, your 3 choices would be, or let's go with this one. It doesn't really matter. You can use either 26, 234. You could use 78, 702. Or you could use 26 and 702. So these 3 choices are why I put a 3 there. Okay, now we get into the new territory, which is this guy. 4 elements we did. Now we have to do 5 elements. Well, when there's 5 elements, interestingly, there's only one way of choosing. For example, if we have, say, this guy, we can only choose 10, 90, and 810. That's the only way of doing it. To choose the maximum and to choose in a way that the rules are satisfied, that no element is 3 times the other. All right, moving right along. If there's 6, well, there's going to be a little bit more complicated. So let's explain with that one. If there's 6 elements, there are 4 ways of choosing. So for example, you can use 4, 36, 324. You can use 12, 108, 972. You can use 4, 36, and 972. Or you can use 4, 1081, and 972. And as you can see, there are 4 of them. That's why I put a 4 there. So I hope this is making sense. And one last one has some good news, that there's only one way of doing it. So for example, if this was the subset, you can only choose 1, 9, 81, and 729. That's it. That's the only way to do it. So that's why there's 1 there. Okay, we are in the final step. We are basically at the point where you calculate n. And just like before, if you remember, with my examples where k is equal to 9 and k is equal to 27, that's the same way I'm going to do it up here for this one. N is going to be, I'll do it in red here, this to this power. So 2 to the power of 302. This to this power. But we don't really need to include that because 1 to the power of 102 is just 1. It's pointless to write that in. So I'll skip that. Then this to this power, that will actually contribute. This to the power of 11, don't need to put that in. 4 to the power of 4, that will definitely contribute. And then 1 to the power of 2, which is just 1. There we go. That's the value of n. And we can simplify this a little bit. Since this is 2 to the power of 2, this basically becomes 2 to the power of 310, 3 to the power of 33. And that is of the form p to the power of a, q to the power of b. And now our final step is to figure out big N, which was p squared plus q squared plus a squared plus b squared. Well, that's going to be 2 squared plus 3 squared plus 310 squared plus 33 squared. That number is 97202. We were asked to find the last 3 digits, 202. So the answer to this is 202, which is choice A, number 25.